In this question, you're provided with the exact nuclear mass for argon-36, and then you're asked for the nuclear binding energy per nucleon. Let me double underline that, because that'll be important at the end of this problem here. Calculating nuclear binding energy is a pain in the butt, and there's a process to it, and I've got it kind of delineated here. We're just going to follow these steps in order. So the first step is to calculate that mass defect. Now we have the actual mass, that's what was provided in the problem, but we need to first get this predicted mass. So you notice that the mass of a proton and neutron is given in the problem, and we should figure out how many protons and neutrons argon-36 has. So argon is atomic number 18, so that means it's going to have 18 protons. So we'll take 18 times 1.00728 AMUs to get the mass of the protons, and then with a mass number of 36, the other 18 is the neutrons, so 18 neutrons, and that's 1.00867 AMUs per neutron, and this will get us the predicted mass. We multiply these together, and this comes out to 36.2871 AMUs, and you're going to want to carry out a lot of sig figs on these calculations here. So now we can get this mass defect by taking the difference between this predicted mass and the actual mass given in the problem. So if we take here the 35.967546 AMUs, that's a 4 by the way, subtract off the 36.2871 AMUs we just calculated, and the difference between those is going to be a negative number. Your mass defects are properly a negative number, but you're only going to use the positive value, the absolute value, later on in the calculation, but 0.319554 AMUs. So that's step number 1. Now if we move on to step number 2 here, now we got to convert this to kilograms. It turns out the whole point of calculating mass defect is to plug it into E equals delta mc squared. But to use that equation, the SI unit needs to be used for mass, and that's the kilogram. So we need to convert that, and I provided you with a conversion here in the problem itself. And so we'll take this mass defect, and 1 AMU is the equivalent of 1.66 times 10 to the negative 27 kilograms. So our AMUs are going to cancel here, and we're going to come out with 5.3046 times 10 to the negative 28 kilograms. Cool, so that's step number 2 done. So from here, we plug this into E equals mc squared. And so in this case, that's that 5.3046 times 10 to the negative 28 kilograms times the speed of light squared. And speed of light is given in the problem here, but probably a value worth memorizing. Comes up in quite a few contexts here. So it's 3 times 10 to the 8th meters per second. Don't forget to square it. It's one of the most common errors in this kind of a problem here. So, but if we do this, we're going to come out with an energy of 4.77 times 10 to the negative 11 joules. So, and this is the total nuclear binding energy, but not per nucleon. So the last step here, we want to change this into per nucleon. So we need to divide this by the actual number of nucleons, the total number of protons and neutrons in the nucleus, which is just the same as the mass number, which is 36 for argon-36. So, and if we do that, we're then going to come out with the correct answer here, 1.33 times 10 to the negative 12 joules per nucleon. There indeed is your correct answer.